Hello, my name is Douglas Fontes. I'm a postdoctoral researcher at the Florida Space Institute of the University of Central Florida. I'll be presenting a numerical simulation of lunar regolith particles interacting with lander rocket at low altitudes. This work is a result of collaboration between the Florida Space Institute and the Granular Mechanics and Regolith Operations Laboratory from NASA Space Center. So it's a collaboration between Philip Metzger, Douglas Fontes, and James Montalvani. This presentation includes an introduction with the goals of the study, general characteristics of the model used in the simulation, results and discussions, final remarks, and the acknowledgements followed by the references. Economic opportunities, scientific knowledge, and colonization are few reasons for future space exploration missions. Return human missions to the moon is the first step for the other missions, including Mars. Before that, it's critical to understand and mitigate the potential damage caused by rocket plume interacting with lunar regolith. As the rocket plume approaches the lunar soil, erosion mechanisms and particle lifting occur, ejecting particles at high speed above 3,000 meters per second, perhaps. At this speed level, particles may damage nearby structures, the lander itself, and orbital objects, as they may reach values higher than the lunar escape velocity. This study presents the results of numerical investigation of the trajectory, velocity, and angle of particles ejected by rocket plumes of a 40-ton lander at low altitudes, 1 to 7 meters in altitude. In comparison with a previous lunar lander sizes, usually around 15,000 kilograms, larger landers will have a higher velocity and denser rocket plume with direct influence on dynamic forces on particles, which will affect the erosion mechanisms. The higher energetic flow increases the potential of damaging nearby structures and the lander during its descending. The main goal of this study was to investigate numerically particle trajectories under the influence of a 40-ton lander at different altitudes. The particle sizes ranged from 1 micrometer to 1 centimeter. The initial radial position of the particles ranged from 1 to 10 meters from the center line of the rocket jet. To obtain some insights of the realistic interactions between rocket plumes and the particulates on lunar environment, we simplify the problem to a physical model defined by some hypotheses, initial and boundary conditions, and define fluid, environmental, and particulate properties. This simplified model is then represented by appropriate transport equations and correlations that can be solved using a numerical model. The numerical solution returns information that can be used to better understand the interactions and properly act on technological issues to reduce risk of damage caused by particles. The physical model consists of a quarter domain given the fluid dynamic and geometric symmetry of the problem. The flow is solved under lunar gravity and near vacuum conditions. The inlet conditions in the numerical domain are associated with the flow conditions to equal the 40-ton lander hovering in lunar environment. The figures shows the main dimensions of the numerical domain and the boundary conditions associated with each surface. Using this physical model, the mathematical model uses the DSMC method to obtain rocket plume flow variables for the 4 altitudes. For solving the particle trajectory, the Lagrangian approach, considering drag and weight forces, uses the rocket plume flow solution through a one-way coupling. We simulated a broad range of particle initial radial positions and sizes to investigate their terminal velocity, angle after the plume flow influence region. In the present study, all particles are placed initially at 0.3 meters above the bottom surface. This strategy was similarly used by Lane et al. In 2008. This strategy ensures that the particles will not be attached to the ground, which has low overlying velocities. In terms of the mathematical and numerical modeling, the rocket plume is solved as particles representing the molecules of combustion products in a stochastic way. We consider that molecules of the combustion products of a stoichiometric reaction of the propellant dinitrogen tetroxide plus iodine 50 for the computational parcels injection through the rocket exit surface according to this equation. The DSMC model considers computational parcels representing statistically several molecules to solve intermolecular and molecular surface collisions. In the present investigation, all simulations use the variable hard sphere molecular model for binary collisions, while the energy exchange between particles and wall surface is solved by the Maxwell thermal model. For the particle trajectory, we implemented a Python code that uses the flow solution to calculate how drag and weight forces act on individual particles. This code solves Newton's second law using fourth-order Runge-Kutta integration and a tracking algorithm to localize the appropriate cell information based on particle position. This slide shows the local Knudsen number fields of the rocket plume for different lander altitudes. Considering a threshold of 0.1, there is a significant region in which the continuum model fails to predict the flow. Thus, a microscopic approach is necessary for the investigated conditions. This slide shows the velocity, magnitude, density, pressure, and temperature fields of the rocket plume. In the velocity magnitude, we can see shock waves in a ball shape beneath the nozzle exit for all altitudes except for a lander at 1 meter. Also, we can observe that a rapid reduction in the flow density with the radial distance from the center line of the rocket jet. This reduction in the gas density and pressure limits the drag force effect on the particles to a certain distance that does not exceed the numerical domain. Due to the drag force, the regolith particles will be ejected from their initial position, reaching high velocities according to the crossed plume flow region. When particles leave the domain, the drag force is negligible because of the fast plume expansion in the almost vacuum environment. Thus, particles at the outside surface of the numerical domain follow ballistic trajectories. The pressure and shear on the bottom surface are important measures to quantify possible erosion and particle lifting mechanisms. As we can see, the pressure is maximum at the corner of the domain, while the maximum shear stress occurs at a certain radius from the center line. This is due to a combined effect of the density and velocity in the boundary layer. Variations of density, velocity, pressure, and temperature with the radial position depends on the shock wave characteristics and lander altitude. These profiles were extracted from a line probe 0.5 meters above the surface. Due to the lack of ambient back pressure, all variables rapidly reduce with the radial position. For density and pressure profiles, there is an inversion of the order of the profiles. Close to the center line, density and pressure are higher as the lander altitude is lower. As the radial distance increases, pressure and density are higher as the lander altitude is higher. This is basically an effect on how the gas expands in different preferential directions as the lander descends. Particle trajectory plotted on a longitudinal plane XY presents lower angles when the lander is at 7 meters in altitude compared to the angles when the lander is at 1 meter in altitude. Larger particles are more likely to bounce than smaller particles, which present a ballistic trajectory inside the domain. The velocity of the particle leaving the numerical domain depends on the particle size, initial radial position, and lander altitude. These figures show the velocities of different particles leaving the numerical domain in terms of their diameter, initial radial positions, when the lander is at 1 and 7 meters in altitude. The maximum particle velocity predicted in this study was around 755 meters per second, which is below the lunar escape velocity. However, a ground surface, including craters, may affect the plume flow, leading particles to high velocity regions of the plume. Particles that go to those regions would reach higher speeds than the lunar escape velocity with greater damage potential. As final remarks, particle velocity is highly dependent on the characteristics of the lander size, altitude, and regolith size and position. As we saw, the maximum velocity of the particles in this study is below the lunar escape velocity. However, different soil topology may drive particles to higher velocities on the plume region. Another effect could also take particles to those high velocity regions, such as particle rolling and bouncing with the ground surface. Handy correlation for the particle velocity was developed is on a paper submitted to the ACTA Astronautica Journal. Thank you for your attention. Those are the references used on this presentation.